listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're going to be checking in with leading industry experts and our very own Worth Electronic technical specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast. Developers of switching regulators and switch mode power supplies, or SMPS, attach great importance to the efficiency of their circuits. Even though their switching regulator may produce a constant output voltage at the end of development phase, a lot of times they encounter unpleasant effects, such as unwanted oscillations at the input. So why does the input of the switching regulator tend to oscillate under certain circumstances? A switching regulator can achieve efficiency of more than 90%. However, the efficiency for conventional switching regulators is usually a lot lower. For high efficiency, we can assume almost loss-free power conversion so that the input power is roughly the same as the output power. However, let's assume that a switching regulator does not produce any power loss and the input power equals the output power. Now, any switching regulator design requires that the output voltage is constant in every operating mode. And even in the event of abrupt load change, it quickly regains its set point without being set in oscillation. So only any change of the voltage on the input side is permitted. However, a constant power ratio between input and output results in the input current of the switching regulator dropping in the event of any rise of the input voltage. Ergo, the input current rises when the input voltage drops. This effect is based on the so-called negative input resistance. This effect is not initially apparent. It's also not expected because the current usually rises proportionally with the voltage. In any case, Ohm's Law describes the behavior of a linear resistance. If a simple voltage divider made of ideal resistors is used, then its output voltage rises when its input voltage is increased. You can find our illustration on attached figure 1 of this podcast. In our case, the input resistance of a switching regulator is not linear, but very nonlinear, and it's also negative. For further demonstration, we would like to consider a voltage divider, which is not constructed from two ideal resistors, but instead from one voltage source with defined internal resistance and a switching regulator with negative resistance. Using this voltage divider, a basic design of the switching regulator and its components is not required here for the closer consideration. If the voltage of the source increases, the current drops, and consequently the voltage drop at the internal resistance of the voltage source. However, the voltage at the switching regulator input increases. The input voltage of the switching regulator is reduced by the voltage drop at the internal resistance of the voltage source. In basic mathematical terms, the constant equals the supply voltage minus the voltage drop. Electronic components such as electrical resistors do not occur in real life with negative values. The real input resistance of a switching regulator is also not negative, but its behavior during change of the input voltage shows a negative resistance, which is based on a mathematical origin. If a tangent is applied to the voltage current curve, its increase of the negative resistance can be determined at any operating point. This is generally defined by the input resistance equals the change in input voltage divided by the change in input current. As the slope of the tangent is negative in this case, the input resistance of the switching regulator is also negative. There is dynamic behavior with negative slope whose differential quotient can theoretically be used as base to determine the negative resistance as numeric value. Attached figure 2 in this podcast is an example that shows this calculation for dynamic behavior. However, in practice and in different literature that you can read, the differential quotient is not determined, but the stationary input resistance is considered. Dynamic behavior is present and, therefore, a different resistance value at each operating point. From a pure mathematical consideration, the stationary resistance is not negative. It's now based on the fact that its dynamic behavior is negative, and it is calculated using a negative sign. Using large signal analysis, the stationary resistance can be approximated with the following assumption of input power equals input voltage times input current. And if the input voltage is further increased, the negative resistance rises. Our attached figure 3 illustrates this mathematical calculation. As much as we would love this to be a clear-cut explanation, the negative resistance is not a persistent state, and it only occurs during a short-term change or a transient at the input of the switching regulator. Once the original operating state is reached again, the negative resistance is no longer representative. A transient combined with a negative input resistance is enough to put the input of the switching regulator in oscillation. A pulsed current flows in the input circuit of the switching regulator. This current should be suppressed to prevent conducted emission interference. So this means an additional input filter is placed before the switching regulator input. In our final attachment figure 4, we see the input impedance Z sub in of the input regulator is formed by the input capacitor, or C sub in, and the negative input resistance, R sub in. The input filter, for example, the WE PD2 or the WE TI filter coil from Worth Electronic, forms a series resonant circuit with the output impedance in the direction of the switching regulator input. The input filter is parallel to the input capacitor and the negative input resistance and can result in oscillation of the input circuit at resonance frequency. However, if a small signal analysis is performed, the voltage source at high frequencies presents a short circuit, whereby the filter capacitor is short-circuited, resulting in only the filter coil still being considered. A high-quality coil is usually selected as the filter coil. Using these coils, the output impedance of the filter is at its highest at resonance frequency and conflicts with the input impedance of the switching regulator. To prevent any oscillation, it's recommended to attenuate the filter to reduce the impedance during resonance. A design tip here is to keep the output impedance of the filter much lower than the input impedance of the switching regulator. Ceramic capacitors are often used in the input circuit, but the problem here is that this results all the more in oscillation of the filter, as ceramic capacitors have negligibly small ESR. This increases the quality of the filter. In theory, reducing the quality could be done by a parallel circuit of resistors, but this isn't exactly a practical solution. It is recommended as a design tip to use electrolyte capacitors here, and they have relatively large ESR. A large ESR can sufficiently reduce the quality of the input filter, whereby the input filter is attenuated and oscillation at the switching controller input is prevented. In conclusion, after extensive examination of the so-called negative resistance, we can come to the understanding that the sign is based on a behavior which can be attributed to the drop of the input current during increase of the input voltage of a switching regulator or a transient. Due to the conducted interference, an input filter is absolutely required, but it should also be attenuated so that the negative resistance is overcompensated and can further prevent any oscillation. Finally, it's recommended not to use ceramic capacitors and to use electrolyte capacitors to prevent unwanted oscillations at the switching regulator input. Attached images are available in most podcast streaming networks. To view all these images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.